In this review video, we'll work through a set of real exam-style Calculus 1 problems on advanced differentiation techniques. These are the same types of problems I used to give my university students to review for their exams, and the examples come directly from my Calculus 1 course videos, just the problem-solving portion without the lecture, so you can stay focused on the examples. You can also download the free PDF of all the practice problems on my website, understandthemath.com. Let's get started. We are now going to go over 4 examples where we're going to differentiate a function using the chain rule. Up here on the right in green, I've placed the formula for the derivative of our composite function f of g of x. The derivative then is just the derivative of the outside function times the derivative of the inside function. In our first example, in addition to using the chain rule, we are going to also use the power rule. Our derivative is then capital F prime of x is equal to the derivative of the outside function, so that's 3, 2x to the 4th plus 5x squared, and then we subtract 1 from 3 and get 2, and then we're going to multiply that by the derivative of the inside function. And that derivative is 4 times 2 is 8, x cubed, plus 5 times 2 is 10, x. Now let's go ahead and simplify. Notice in this expression right here, we have a 2 that's common to both terms, and we also have an x common to both terms. So let's go ahead and let's pull that out and let's rearrange some terms. So this is 3 times 2x times 2x to the 4th plus 5x squared squared times what remains after we pull out the 2x, and that's going to be a 4x squared plus 5. When you're taking a derivative using the chain rule, it's customary when you write your final answer to write your answer as your constant first, and then smaller powers of x, and then bigger powers. So we are going to rewrite our answer as 6x times 4x squared plus 5. We're putting that one first because it's raised to the first power, and then we're going to put down 2x to the 4th plus 5x squared quantity squared. And then that's our final answer. Let's now look at our second example. In this example, in addition to the chain rule, we are going to use the power rule and the product rule. Our function has 2 terms, which is why we're going to need to use the product rule. Here's the first term, and then here's the second term. We're going to write our derivative f prime of x as our first term, x to the 4th minus 1 quantity cubed, times the derivative with respect to x of our second term, x cubed plus 1 to the 4th, plus our second term, x cubed plus 1 to the 4th, times the derivative of our first term, x to the 4th minus 1 quantity cubed. Now we're going to use the chain rule. We have the first term, x to the 4th minus 1 cubed. Using the chain rule for this derivative, we bring down the 4, and then we have an x cubed plus 1. Subtract 1 from the 4, and that's 3. Now we have to multiply by the derivative of what's inside, and that is 3x squared. Now let's go to the second piece. We're going to add x cubed plus 1 to the 4th, and then we use the chain rule and take the derivative of x to the 4th minus 1 quantity cubed. So we bring down the 3, and then we have an x to the 4th minus 1 squared, and then we multiply that by the derivative of what's inside, which is 4x cubed. Now we have to simplify all of this. I think it's easiest if we simplify both terms first and then see what combines. Our first term is 4 times 3, so that's 12. We have an x squared, and then we have an x to the 4th minus 1 cubed, and an x cubed plus 1 cubed. And then for our second term, we also have a 4 times a 3, so we have 12. And we have x cubed, and then we have an x cubed plus 1 to the fourth, and then x to the fourth minus 1 squared. Now let's see what both terms have in common. They both have a 12, so we can pull the 12 out. And then they both have an x term, and we can only pull out the lowest x term, so that's going to be x squared. So we pull out x squared. And then they both have an x to the fourth minus 1, and we can pull out the lowest power, which is a squared power. So this is x to the fourth minus 1 squared. And then lastly, they both have an x cubed plus 1, and we'll pull out the lowest power, which is a 3. So this is x cubed plus 1 cubed. Now we have to see what's left. In our first term, we're going to have one more x to the fourth minus 1. And then in our second term, we are going to have an extra x. And then we are going to have an extra x cubed plus 1. Let's go ahead and let's simplify this part. This is x to the fourth minus 1 plus x to the fourth plus x. So this is 2x to the fourth plus x minus 1. And we're going to combine all of this with this. This gives us an answer of 12x squared times x to the fourth minus 1 quantity squared times x cubed plus 1 cubed times 2x to the fourth plus x minus 1. And that took a while, but that is our final answer. For our third example, I chose a function that is going to require us to use, in addition to the chain rule, the power rule and the quotient rule. Notice that our function has a numerator and a denominator. So that clues us in that we have to use the quotient rule. Let's go ahead and take the derivative. F prime of x, using the chain rule first, is 5 times x squared over x plus 1 to the fourth. That's the derivative of the outside function. And then we're going to multiply this by the derivative of the inside function, which is our function that has the two pieces, x squared and x plus 1. This is equal to 5 times x squared, all divided by x plus 1, raised to the fourth power. And now for the second piece, we are going to use the quotient rule. So we have our bottom term, x plus 1, times the derivative of our top term, which is 2x, minus our top term, times the derivative of our bottom term. The derivative of x plus 1 is just 1. So we multiply that by 1. And then all of this gets divided by the bottom term squared. Let's go ahead and let's see if we can clean this up. This is 5 x squared over x plus 1 to the fourth. In the numerator, we have 2x squared plus 2x minus x squared. And then in our denominator, we have x plus 1 squared. Now we have to combine everything. For this first term, let's go ahead and let's multiply it out, because notice that we have an x plus 1 in the denominator of both of these terms, and we're going to need to combine that. So we're going to write this as 5 times x squared to the fourth. You just take the exponents and you multiply them. So 2 times 4 is 8. And then in the denominator, we have an x plus 1 to the fourth. And then for our second piece, we have 2x squared minus x squared. So that's x squared plus 2x, all divided by x plus 1 squared. This gives us 5x to the 8th. And then the x squared plus 2x, let me highlight that so you can see what I'm talking about. For that piece, we can pull out an x and write this as x plus 2. And then in our denominator, we have two functions multiplied, which means we add the exponents. So this becomes x plus 1 to the 6th. Now we're almost done. We can combine our x's. So we have a 5x to the 9th, and we have an x plus 2. And in our denominator, we have our x plus 1 to the 6th power. And that is our final answer. Hang with me. We have one more to do, and it's different because it involves trig functions, and it also has an inner, middle, and outer term. Here's our fourth example. We are going to take the derivative of sine of cosine of tangent x. Since this function has an inner term, a middle term, and an outer term, I went ahead and wrote down the formula for our derivative. It is going to be the derivative of the outside function times the derivative of the middle function times the derivative of the inside function. Our derivative is going to be f prime of x. The derivative of the outside function is the derivative of sine, which is cosine. So we have cosine of tangent x. Now we're going to multiply by the derivative of the middle function, which is our cosine. The derivative of cosine is minus sine, and inside that function is tangent x. And then lastly, we're going to multiply by the derivative of the inner function, which is tangent. The derivative of tangent x is secant squared x. Now we're going to rewrite all of this, and we are going to put our function that just has one piece first, and then the one that has two pieces, and then the one that has three pieces. So we write this as minus secant squared x times sine of tangent x times cosine of tangent x. And that's our derivative. In examples 1, 2, and 3, we are going to find dy dx by implicit differentiation. I have written down the 3 steps that we can follow just to make it easier, and we will go through these steps as we walk through our examples. Let's look at our first example. We are given the equation 1 plus x is equal to sine of xy squared. We're going to start by differentiating both sides of the equation with respect to x. So this is d dx of 1 plus x is equal to d dx of sine of xy squared. The derivative of 1 is 0, and then the derivative of x with respect to x is 1. And then on our right-hand side, the derivative of sine is cosine. So we have cosine xy squared times the derivative of what's inside. On our left, we have 1, and then on our right-hand side, we have cosine xy squared. And now we're going to use the product rule. Here's our first function, and here is our second function. The product rule tells us that the derivative is going to be the first, which is x, times the derivative of the second, which is 2y times dy dx. Remember, whenever you differentiate a y, you have to multiply by dy dx, plus our second function, y squared, times the derivative of our first, which is just 1. Since we eventually have to solve for dy dx, let's go ahead and let's multiply everything through on the right-hand side. This gives us 1 is equal to 2xy cosine xy squared. Notice I just rearranged the terms, and then we have a dy dx plus y squared cosine xy squared. It is standard to put a variable before a trig function. Now for our second step, we are going to get everything with dy dx on one side and everything else on the other side. So I am going to take our y squared cosine xy squared, and I'm going to bring it to the left. So this gives us 1 minus y squared cosine xy squared is equal to 2xy cosine xy squared dy dx. Now we're going to solve for dy dx, and that is our third step. So let's divide everything by our 2xy cosine xy squared. I am going to go ahead and flip both sides just so our dy dx is on the left. So we have dy dx is equal to 1 minus y squared cosine xy squared, all divided by 2xy cosine xy squared. And that is our answer. Let's now look at our second example. We are given the equation the square root of x plus y is equal to 1 plus x squared y squared. Just like we did for the first example, we are going to start by taking the derivative with respect to x of both sides. I am going to rewrite our square root as x plus y to the 1/2. And then on our right-hand side, we have d dx of 1 plus x squared y squared. Let's go ahead and now take our derivative. The derivative on our left is 1/2 x plus y to the minus 1/2 times the derivative of what is inside. That's the derivative of x plus y. So this is 1 plus dy dx. And then on the right-hand side, the derivative of 1 is 0. And then we have to use the product rule. We have a first function and a second function. So our derivative is going to be the first function x squared times the derivative of y squared, which is 2y dy dx, plus our y squared times the derivative of x squared, which is just 2x. Now we have to do some algebra simplification. The first thing I'm going to do is I'm going to take our x plus y to the minus 1/2, and I'm going to bring it to the denominator and make it a square root. So on our left-hand side, we have 1 plus dy dx in the numerator, and in our denominator, we have 2 times the square root x plus y. And then on our right-hand side, we have 2x squared y dy dx plus 2xy squared. We are working towards solving for dy dx, and I think the easiest way to do that is to go ahead and get rid of our denominator on the left-hand side. So I am going to multiply both sides by 2 times the square root of x plus y. This gives us 1 plus dy dx on the left. And then on the right, we have for our first term 4x squared y square root x plus y times dy dx. And then for our second term, we have 4xy squared times the square root of x plus y. Now we get to go on to our second step. We are going to put everything with dy dx on one side and everything else on the other side. Let's put this term and this term on the left-hand side. So we have dy dx minus 4x squared y square root of x plus y times dy dx. And then we're going to take our 1 to the right-hand side. So our right-hand side is 4xy squared square root of x plus y minus 1. Now let's go ahead and factor out a dy dx. So we have dy dx times 1 minus 4x squared y square root x plus y is equal to 4xy squared square root of x plus y minus 1. Now for our third step, we can go ahead and solve for dy dx. So we're going to divide both sides by this expression. This gives us dy dx on the left is equal to 4xy squared square root x plus y minus 1, all divided by 1 minus 4x squared y square root x plus y. When I was working through this problem, I looked at this when I got to this point and I thought, oh, maybe those terms cancel. But then I realized that in the top term, we have an xy squared, and then in the bottom term, we have an x squared y, so they are not the same. So this is our final answer. Let's now look at our third example. This one has a trig function in it. In this example, we're going to be finding dy dx for the equation tangent of x minus y is equal to y divided by 1 plus x squared. Let's start by taking the derivative with respect to x of both sides. D dx of tangent x minus y is equal to d dx of y divided by 1 plus x squared. Now we can go ahead and take the derivative. The derivative of tangent is secant squared of x minus y times the derivative of what's inside, and that derivative is 1 minus dy dx. And then on our right-hand side, we have a quotient. We have a term in the numerator and a term in the denominator, so we are going to use the quotient rule. The quotient rule tells us that the derivative is the bottom term, 1 plus x squared, times the derivative of the top, which is dy dx, minus the top term, which is y, times the derivative of the bottom term, which is 2x. And then we could divide all of that by the bottom term squared. Now we need to simplify this. I think it's easiest if we don't have denominators, so let's multiply both sides of our equation by 1 plus x squared quantity squared. This gives us 1 plus x squared squared, secant squared, x minus y, times 1 minus dy dx. And then on the right-hand side, we have a 1 plus x squared dy dx minus 2xy. Since we want to find dy dx, I think the best thing that we should do is multiply everything out so we can separate the terms out. On the left-hand side, we have 1 plus x squared squared, secant squared, x minus y, minus 1 plus x squared squared, trying to write small here, secant squared, x minus y, dy dx. And on the right-hand side, we don't have to do anything, and we just write this as 1 plus x squared dy dx minus 2xy. Now what we're going to do is we are going to pull everything with a dy dx onto one side and everything else on the other side. I'm thinking because we have a negative right here, it's probably going to be best to pull the dy dx terms to the right and everything else to the left. So let's write this as 1 plus x squared squared, secant squared x minus y. And we're going to pull the 2xy from the right to the left. So we add 2xy. And then on the right, we have a 1 plus x squared dy dx. And then we're going to add 1 plus x squared squared secant squared x minus y dy dx. I think the hardest thing of implicit differentiation is solving for dy dx. And I just realized that this was our second step, so I'm going to put a 2 there. Now we need to solve for dy dx. So let's clean up this right-hand side. I am going to pull out a dy dx from both terms, and then notice that each term also has a 1 plus x squared. So let's go ahead and let's pull that out too. 1 plus x squared, and then we're left with a 1 plus a 1 plus x squared secant squared x minus y. Now for our third step, we are going to solve for dy dx, and let's switch sides just so that the dy dx is on our left. So on our left, we have dy dx. And on our right, we have the term that was on the left, 1 plus x squared squared, secant squared, x minus y, plus 2xy. Now we're going to divide by all of this. And that is 1 plus x squared times 1 plus x squared secant squared x minus y. And there is our final answer. Notice that we could not cancel out a 1 plus x squared because this term didn't have the 1 plus x squared with it. We're now going to look at a different type of problem. For this problem, we are going to find the equation of the tangent line to this curve at the point 2, 1. This curve is called a cardioid because it's shaped like a heart. And what we're doing, if you look down here at our graph, is we are finding the equation to the tangent line of this curve at this point right there. Let's start by writing down what the equation of our tangent line is. It is y minus y1 is equal to our slope times x minus x1. Our slope, m, is the derivative of y with respect to x at the point x is equal to x1, which in our problem is equal to 2, and then y is equal to y1, which is 1. Let's now find our dy dx. Looking back up at the equation in the upper right that's highlighted in yellow, we are going to take the derivative with respect to x of both sides of that equation. So we have the derivative with respect to x of x squared plus y squared minus 1 quantity squared is equal to the derivative with respect to x of 4 times x squared plus the quantity y minus 1 squared. Looking at our left-hand side, we are going to use the power rule to find the derivative. So that is 2 times x squared plus y squared minus 1 times the derivative of what's inside, which is 2x plus 2y times dy dx. And then on our right-hand side, our first derivative is 4 times the derivative of x squared, which is 2x. So we have a 4 times 2x. And then don't forget that that 4 multiplies through both terms. And I just realized that I need an extra parenthesis there. So we have a 4 times the derivative of this term, which is 2 times y minus 1 times dy dx. Now, I'm going to show you something here that makes things a lot easier. We could go through all the algebra and solve for dy dx, but we don't need to because we are going to be plugging in that x is equal to 2 and y is equal to 1. So let's go ahead and let's do that now. We are going to plug in x is 2 and y is 1, and that is just going to make things so much easier. So we have 2 times 2 squared, which is 4, plus 1 squared, which is 1, and then minus 1. And then we have 2 times x, so that's 4, plus 2 times y, which is 2 times dy dx. That's what we're solving for. And then on the right, we have 4 times 2, which is 8, times x, which is 8 times 2, so we have a 16. And then we have an 8, and y minus 1 is actually 1 minus 1, so that's going to be 0 times dy dx. Let's see what we have on our left-hand side. We have an 8 times 4 plus 2 dy dx. And then on our right, we only have 16. Let's divide both sides by 8. So we have 4 plus 2 dy dx is equal to 2. And this gives us 2 dy dx is equal to 2 minus 4, which is minus 2. And if we divide by 2, we can see that dy dx then is equal to minus 1. We are going to take this answer then and go ahead and plug it in for our slope. Let's go ahead and let's write down our equation again. We have y minus y1 is our slope, x minus x1. y1 is equal to 1, so we have y minus 1. Our slope we found to be negative 1, and then we have an x minus x1, which is x minus 2. Let's go ahead and let's multiply things through. This is y minus 1 is equal to minus x plus 2, which gives us that y is equal to minus x plus 3. And that is the equation of our tangent line to our curve. Let's go back up to the top here because I want you to notice that our answer, y is equal to minus x plus 3, matches with that pink line. It has a slope of negative 1 and it has a y-intercept of 3. In each of these examples, we are going to find the derivative of the given function. In our first example, our function is y is equal to the inverse tangent of 4x quantity squared. On our left-hand side, we have dy dx. And to find the derivative of the right-hand side, we are going to use the power rule. So we have 2 times inverse tan of 4x to the 2 minus 1, which is just 1, times the derivative of what's inside. So let's just write down, we're going to be taking the derivative of inverse tan of 4x. Over here on the right, I'm going to write down that the derivative with respect to x of inverse tan of u is equal to du dx on the top, and on the bottom you have a 1 plus u squared. Let's now go back to our equation and put in that formula. On our left-hand side, we still have dy dx, and then on our right, we have 2 times inverse tangent of 4x. And now we're going to take the derivative of inverse tan of 4x. This is our u. So we're going to take the derivative of 4x, which is 4. And then in our denominator, we're going to have a 1 plus u squared. So this is 1 plus the quantity 4x squared. Let's now combine our constants. So we have an 8 inverse tan of 4x. And then in the denominator, we have a 1 plus 16x squared. And that's our answer. That wasn't too bad. Let's now look at our second one. For our second example, we are going to be taking the derivative of the inverse sine of 3x plus 1. Let's go ahead and write down the formula for the derivative of inverse sine. So the derivative with respect to x of inverse sine of u is du dx on top, And then in our denominator, we have the square root of 1 minus u squared. So our derivative is dy dx is equal to the derivative of u. This is u, 3x plus 1. So the derivative of 3x plus 1 is just 3. That goes on the top. And then in the denominator, we have the square root of 1 minus 3x plus 1 squared. We could multiply out our denominator, but it's standard to just leave it in that form. And we'll highlight this because that is our final answer. Let's now look at our third example. We are going to take the derivative of the function y is equal to x times inverse secant of 2x. On the left, we are going to have dy dx. And then notice that we have two functions here on the right. We have an x and we have an inverse secant of 2x. So we are going to use the product rule. So this is the first times the derivative of the second. So I'm just going to write this as the derivative of inverse secant of 2x plus the second, which is inverse secant of 2x, times the derivative of the first. The derivative of x is just 1. Now let's go ahead and let's write down our formula. The derivative with respect to x of inverse secant of u is du dx, all divided by absolute u times the square root of u squared minus 1. I always tell my students the one way to remember this is if the u is here, it's also here, and you have u squared minus 1 instead of 1 minus u squared. I don't know if that's going to help, but hopefully it will. So we have dy dx is equal to x. Now we're going to take the derivative of inverse secant of 2x. The 2x is our u. So we're going to take the derivative of 2x, and that goes on top, so that's a 2. And then we're going to divide that by absolute 2x times the square root of 2x squared, so that's a 4x squared. The absolute goes away because we're squaring it, and then we subtract 1. It looks like our 2's can cancel, so we're going to write this as x divided by absolute x square root 4x squared minus 1. And we did it. There is our final answer. Let's now walk through 4 examples, and in each example, we are going to differentiate the given function. Here's our first function. We are going to differentiate the natural log of sine of x. Our derivative we can write as f prime of x, and the derivative of the natural log of sine x is 1 over u, and u is sine x, so we have 1 over sine x, times the derivative of sine x, which is cosine x. This gives us cosine x over sine x, so our answer is cotangent x. Let's now look at our second example. We're going to differentiate the function x times the natural log of x squared plus 1. Notice that f of x contains two functions, x and the natural log of x squared plus 1. So to take the derivative, we're going to use the product rule. This gives us f prime of x is the first, which is x, times the derivative of our second function. The derivative of the natural log of x squared plus 1 is the derivative of x squared plus 1 on top, which is 2x. And then we just put the x squared plus 1 in the denominator. And then we have our second function, natural log x squared plus 1, times the derivative of our first. The derivative of x is just 1. So we can write our answer as 2x squared, all divided by x squared plus 1, plus natural log x squared plus 1. And we'll go ahead and we'll highlight that answer. Let's now look at our third example. We are going to differentiate the function f of x is equal to the natural log of 3 divided by x. Because the x in this function is in the denominator, I'm going to start by rewriting our function as f of x is equal to the natural log 3x to the minus 1. That's just going to make it easier to take the derivative. Our derivative f prime of x then is the derivative of what's inside, so that is minus 3x to the minus 2, all divided by what's inside, which is 3x to the minus 1. The 3's are going to cancel, and our top term I'm going to write as minus 1 over x squared, and then our bottom term is 1 over x. To simplify this, we can just multiply the top and the bottom by x, so we get an answer of minus 1 over x. Let's now look at example 4. This one has a common log. We are going to take the derivative of log base 5 of 2x squared plus 7. Our derivative, f prime of x, is the derivative of what's inside. The derivative of 2x squared plus 7 is 4x, all divided by what's inside, which is 2x squared plus 7, times natural log of 5. When you have a common log, you always have to divide by the natural log of the base. And we actually don't need to simplify that anymore, so that is our final answer. Let's now walk through 2 examples where we are going to use logarithmic differentiation to find the derivative of the given function. The first function that we're given is y is equal to x times x squared plus 1, all divided by the square root of x plus 1. Our first step is to take the natural log of both sides of the equation. So we have ln y on the left, and on the right we have ln of x times x squared plus 1, all divided by the square root of x plus 1. Our second step is to work on the right-hand side and simplify that using the laws of logarithms. So our left-hand side stays the same, ln y. The laws of logarithms are going to help us break up our right-hand side. So we're going to write this as ln x plus ln x squared plus 1. You use a plus whenever things are multiplied, and then when things are divided, you use a minus, so we have minus ln of the square root of x plus 1. I'm just going to remind us here that the square root of x plus 1 is x plus 1 to the 1/2. So we can do one more step of simplification, and we're going to pull that 1/2 out in front. So this becomes ln x plus ln x squared plus 1 minus 1/2 ln x plus 1. Now we're ready for step 3. Step 3 tells us to take the derivative of both sides of the equation because we want to find dy dx. So we have the derivative with respect to x of ln y on the left, and on the right we have the derivative with respect to x of ln x plus ln x squared plus 1 minus 1/2 ln x plus 1. The derivative of ln y is going to be the derivative of what's inside, so that's dy dx, all divided by what's inside, which is y. And on the right-hand side, we're going to have 1 over x plus the derivative of ln x squared plus 1, which is the derivative of what's inside, which is 2x, all divided by what's inside, x squared plus 1, minus 1/2 times the derivative of the natural log of x plus 1, and that's just the derivative of x plus 1 on the top, which is 1, and then our x plus 1 in the denominator. I'm going to go ahead and copy this, and we'll take this with us to the next page. Now we're at step 4, where we are going to solve for dy dx. So we're going to take the y that's sitting in the denominator and take it to the right-hand side. So we have dy dx is equal to y times 1 over x plus 2x, all divided by x squared plus 1, minus 1 over 2 times x plus 1. Now, the last thing we have to do is substitute back in what y is. So we have to go all the way back to our original function and plug that in. So we have dy dx is y, which was x times x squared plus 1, all divided by the square root of x plus 1, times what we just had, 1 over x plus 2x over x squared plus 1 minus 1, all divided by 2 times x plus 1. And it's long, but that is our final answer. Let's now look at our second example. This is an example where we have a function raised to a function. And the only way to take the derivative is to pull that function out of the exponent by using logarithms. Let's start with step 1. Step 1 tells us to take the natural log of both sides. So we have ln y is equal to ln of x sine x. Step 2 is to simplify our right-hand side. So we have ln y is equal to sine x times ln x. Whenever you have an exponent, you can just bring it right out in front. Step 3 is to take the derivative of both sides. So we have d dx of ln y is equal to d dx of sine x times ln x. The derivative of ln y is the derivative of what's inside, which is dy dx, all divided by what's inside, which is y. And then on our right-hand side, we have a product. Here's our first function, and here's our second function. So we're going to use the product rule. So we're going to have the first, which is sine x, times the derivative of our second function. The derivative of ln x is 1 over x, plus our second function, ln x, times the derivative of our first. The derivative of sine x is cosine x. Now for our fourth step, we just have to solve for dy dx. So we have dy dx is equal to y times sine x over x plus ln x times cosine x. And then our last step, which is easy to forget, is to go ahead and substitute back in what y is. Y was x sine x. And then we multiply this by sine x over x plus ln x times cosine x. And that's our final answer. That's all for this exam review. I hope it helps you as you prepare for your exam.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.